Right, these are the energy introduction slides. So the first thing that we started off talking about is that if we're looking at a Nerf gun firing a Nerf dart. Well, Newton's third law tells us that there's a force acting on the dart and a force acting on that Nerf gun. Now, so which object, if either, exerts a larger force and magnitude to the other object? We know that for every action, there's an opposite and equal reaction. There's going to be an equal force applied to the dart as it is to that gun. Which object applied that force first? Well, force pairs are simultaneous, which means they started at the same time. Well, which object applied that force for a longer period of time? Well, the time interval is going to be the same because force pairs are simultaneous, so they're applied for the same amount of time. Now, which object experiences a larger impulse? Well, if you look at that equation over there, we know that impulse is force times the time interval that force is applied. Well, we know that the force applied to each object is the same, and we know the time interval that force was applied is going to be the same. So we know that the impulse applied to each object is going to be the same. So which object experiences a larger change in momentum? Well, we know that change in momentum is impulse. So they're both going to experience the same change in momentum. Now, this is sort of the crux of the whole thing. Well, why is the effect of the same impulse different, even though all of these are going to be the same to the dart and the gun? Well, if we look at that, we know that the force and the time interval that force is applied is the same. However, that gun has a much larger mass, so the change in velocity must be lower than the dart. That's why the dart goes so fast, because it has such a low momentum. So let's take a look at this even further. So what is the total combined momentum of both the Nerf gun and the dart before the launch, before it gets fired? It's going to be zero because they're not moving. Right? That's how we know momentum is mass times velocity. And what is the total combined momentum of both the Nerf gun and the dart after the launch? It's going to be zero. You cannot create or destroy momentum. So if you started with zero, you have to end with zero. So what could you say about the magnitude of the momentum of the dart and the magnitude of the momentum of the Nerf gun after the launch? Well, we know that, well, you started with zero, end with zero, so the momentum going forward is going to balance out with the momentum going backwards because it has to be zero. That Nerf dart is going to have the same momentum as the Nerf gun after it's fired. But here's the question, though. Now, when given the choice between firing that Nerf gun, why would you choose to fire it and not be hit with the dart? Why does it seem like the dart is going to hurt you more? So that brings us to this original question, though. Is momentum enough? Is there something more than momentum that can describe what's happening there? So we did the lab, is momentum enough? So in this lab, we rolled different objects down a blue ramp. And in the first part, what we did was we rolled down different objects of different mass from the same starting point, notch number 3. So they're all going the same velocity. And the next part, we rolled the same object, so that the metal marble down each of these ramps. So we're only changing the velocity. And this is what we got. We were looking at the graphs. So these are the graphs of mass versus distance. We're seeing how far that those objects would push a cup on the table. So if we look at this, let's look at the mass let's look at both these graphs and compare and contrast. How are they similar? How are they different? Well, they both have a positive like slope. They both have a positive, they both increase. So yes, if you increase the mass of that object, it's going to increase how far that cup is pushed. If you increase the velocity, well, it's also going to increase how far that cup is pushed. Well, how are they different? Well, they have different shapes there. So you can see here that the top one is a straight line and the bottom one is sort of curved a little bit. So let's look at the mass versus average distance. So if we compare that top graph to the bottom graph, we know that it's going to be a linear equation, y equals x. And you can even see the equation of the mass versus distance one and the r squared. How close are those values to that trend line? You can see that they're fairly close. And it's going to be a linear curve. Now let's look at the velocity versus distance. Well, notice that it's a y equals x squared relationship. So then there's the equation on the graph there. It's going to be an x squared relationship. And that means that it's going to be curved a little bit. So let's look at this big question that sums up this entire lab. If you want to push the cup farther, would it be more efficient to increase the mass or the velocity of the object hitting it? Explain your answer. So what variable, if increased, increases the distance cup pushed more? So well, let's look at what type of graphs they are. Well, the mass versus distance is a linear relationship. Velocity versus distance is a y equals x squared relationship. So it's going to be more efficient to increase the velocity because it goes up at an exponential rate. So there's something more than momentum here. So let's answer this question. Does this rubber band contain a force? So if you have a rubber band in your hand, you ask yourself, well, does it contain a force? If you stretch the rubber band back and you like point it at something, does that contain a force then? What about a Snickers bar? Does that contain a force? What about a battery? Does that contain a force? It's sort of hard to say whether they contain a force, but you know that they all contain something. You cannot possess a force. You can exert a force, but you cannot possess it. So they all contain something. Everything over there, they contain something. Now, I'll give you a hint. It begins with an N and ends in a G. Energy, right? Little joke there, right? Energy. They all contain energy. Now, energy is a very hard concept to grasp around it. And I always compare energy to the color red. So just think about trying to describe the color red to somebody without naming an object, showing, or pointing to anything. So think about trying to describe the color red to somebody who's been blind their entire life. It's very difficult, but you can recognize it, but you can't touch it, taste it, hold it, smell it, hear it. You can't really even explain it very well. Energy, like inertia, is something that a body possesses, but it's not something that's tangible. So energy is the capacity to do work. Now, work is a scientific term that we're going to learn about later. Now, all forms of energy are scalar, which means only magnitude, no direction. So the unit for all forms of energy is the Newton meter, or also known as the joule. So if you apply a Newton of force over a meter, well, that energy that's expended was 1 joule of energy. Now, there are 4 ways of storing energy, and these are broken up even further, and we're going to make a chart that shows these. We have potential energy, you have kinetic energy, you have internal energy, and you have rest mass. So the first type of energy we learn about is a form of potential energy, gravitational potential energy. Now, gravitational potential energy is stored capacity to do work due to the of location in a gravitational force field. Now, it depends on 3 things: the object's mass, the gravitational strength, and how high that object is raised. And you can see the equation over there. You just multiply the mass times gravity times height. And on Earth, well, the Earth gravity we use is uh, 9.8 meters per second squared. Now, in this class, we're just going to use 10 meters per second squared just to keep the math nice and easy. And all you do is you multiply them all together. So there's another form of potential energy, and it's called elastic potential energy. Now, elastic potential energy is the stored capacity to do work due to a location in an electric force field. So it's like stretching the bonds in those atoms. Now, it depends upon 2 things: the spring constant. So what material is that band made out of? What we're stretching made out of? And the displacement. Well, how far was that band stretch? Or it could be like a bouncing object. An object falls down, it compresses a little bit like a bouncy ball. That energy is stored as elastic potential energy, then it's released to make that ball go upwards. So it's energy. It's like the stretching or compressing. Now let's answer this question though: how could a ping pong ball hurt you despite its low mass? Well, let's look at kinetic energy. So we define energy due to the motion of an object as kinetic energy. Now, the thing is that kinetic energy depends not only on the velocity of the object, but also its mass. And you might be thinking, well, that's just momentum. Momentum is mass times velocity. Well, as we saw in the Is Momentum Enough lab, there's something about that velocity. The velocity had a larger effect in pushing that cup. And you can see in that equation there for kinetic energy. Kinetic energy is 1/2 times mass times the velocity squared. The velocity has a much larger effect on the amount of kinetic energy an object has than the mass. And you can see that in how it affected that because, well, it's an exponential rate when you increase the velocity. So now let's talk about other forms of potential energy. So this is chemical potential energy. It's not mechanical energy. Now we'll talk about what mechanical energy is later, but chemical potential energy is the energy stored in the electric bonds between atoms. So these are the types of energy that's stored in like gasoline. You can break those bonds and you can drive a car with it. You can, if you look at a battery, right? That's the chemical potential energy. The food that you eat, that's chemical potential energy stored that your body turns into other forms of energy. So let's talk about another question though. Why is it easier to stand in the cold air than jump into cold water, even if they're at the same temperature? So think about it this way. If you've ever been in a sauna, you know it's very hot, but you can sit in there for 10, 15, maybe even 20 minutes without being hurt. But if you stick your hand in boiling water, it's going to burn your hand almost instantly, like maybe half a second, and then you pull it out. Well, they're both at very high temperatures, but one of them really hurts you and the other, well, you can stay in there for a longer period of time. Here's another thought experiment. If you're ever cooking something in the oven and you open up the oven, that air is gonna like be at 450 degrees and it hits your face. You pull back, but you're not seriously injured. But if you grab the metal plate in there, it's gonna burn your hands, but they're both at the same temperature. So why does one burn you seriously, but the other just sort of makes you take a step back? Well, this is internal energy. So internal energy is the combined potential and kinetic energy of the atoms and molecules within an object. So it's like how much energy can that substance store? So temperature is not directly proportional to internal energy, since temperature measures only the average of translational kinetic energy part of internal energy. So temperature is kind of a part of internal energy. And you can see that atoms can do a lot of different things other than just move back and forth, up and down. That that's temperature. Like how fast the average speed of those molecules zooming around. Well, atoms can do a lot more. They can hold energy different places, and you can see here those bonds can stretch. They can like vibrate in all different axes. Well, all these places that atoms and molecules can store that energy, that's internal energy. So you can see that gases don't have a lot of places to store energy, but liquids and solids, well, they do. They do have a lot of places to store that internal energy. That's why boiling water will hurt your hand a lot more than like the air in a sauna or in an oven. Also with like jumping into cold water, well, there's a lot more room for it to store that energy that water has, so it's going to take your heat a lot faster than air, because air doesn't have a lot of places to take that heat energy away, so you can stay out in the cold longer in the air than you would if you jumped into the water. So two objects with the same temperature do not necessarily have the same internal energy. So you can see here that temperature is kind of a part of internal energy. Now let's answer this question: how does the sun keep generating its energy? Well, that brings us to rest mass, right? Well, rest mass is the energy stored in the mass of all matter. And you can see Einstein's famous equation, E equals mc squared. That's the energy stored in mass. Mass, like matter, is energy. Energy is matter. That's what Einstein said. They're interchangeable, right? Matter is a form of energy, and there's a lot of energy stored in rest mass, and that's like nuclear energy, right? The energy that we get. Now, almost all forms of energy that we interact originated from the sun's rest mass, right? With the exception of like geothermal, which comes from underneath the ground, and like our own nuclear reaction, which is also getting energy out of the matter of like the nuclear components, right? So this is our chart, right? That we're going to fill out, and you can see here that gray is energy that we'll not be learning about this class at this time. There'll be units later on that. Red is non-mechanical energy. Blue is mechanical energy, which is energy that we're going to talk about moving forward. And dash lines, those are forms of potential energy. So uh, this just helps us keep track of all the types of energy. But moving forward, we're just going to talk about, we're really going to deep dive into that mechanical energy. So now that we've talked a lot about energy, let's answer this question. What can energy do that momentum cannot? So to answer this, we did collision carts 2. So if we look at this, this is the exact same lab that we did with momentum, except now we're calculating the kinetic energy before and after all these types of collisions. So you can see the first two are an explosion. Well, the next one's going to be an elastic collision, and the next one is an inelastic collision. So let's go ahead and answer these questions. Well, what do you notice about the total combined kinetic energy before and after the collisions in all the simulations? Well, if we look at this, you can see here in the explosions, well, you start out with less energy than what you ended with. So, like, there's more energy there. If we look at the elastic collision, it's the same. In the inelastic collision, well, you have more energy before the collision, or kinetic energy before the collision, than after. So it's sort of all over the place, depending on what type of collision or explosion we're talking about. That's going to change the amount of kinetic energy before and after. That's where it differs from momentum. So let's look at the simulations for elastic collision and inelastic collision in terms of kinetic energy. Define elastic collisions and inelastic collisions. So let's take a look at that, right? So in an elastic collision, you'll notice that, well, kinetic energy is conserved, right? It started with 50, and after the collision, there was 50 joules. Where it changed, or where that energy was, well, that changed, but the total amount did not. But in inelastic collision, well, you started with 50 joules, and there's less after the collision. So we'll deep dive into that a little bit more. So look at the first explosion simulation. What's the total kinetic energy of both the carts combined before the explosion? The carts are in motion after the explosion, which means they have kinetic energy. Where did this kinetic energy originate? What caused the carts to move? So if we look at the explosion, you'll notice that, well, it started with 0 and you ended with 75 joules. So that energy, well, what caused that motion? What caused that kinetic energy? And it was going to be that explosion. That explosion pushed those carts away and cause that kinetic energy. So now let's look at this. Momentum can be transferred from one object to another. Look at the elastic collision simulation. Can energy be transferred from one object to another like momentum? So if we look at that elastic collision, well, yeah, the red cart had more of that kinetic energy before the collision. After the collision, the blue cart had all of the kinetic energy in that, but like none of it was created or destroyed. It was just transferred from the red cart to the blue cart, where the blue cart had all that kinetic energy. So yes, energy can be transferred from one object to another, from one place to another. Now let's look at this final uh, final one. So energy, like momentum, is conserved, which means it cannot be created or destroyed. Does the data support this? Well, it doesn't really support it because in all of them, yeah, the elastic collision, I had the same amount before and after, but in all the other ones, well, the explosion, I had more kinetic energy after the explosion than I did before. In the inelastic, I had less after the collision than before. So there is one thing that can be done to energy, but cannot be done to momentum. What can energy do that momentum cannot? So, and I give you a hint here. How many forms of momentum are there? Only one. We didn't learn about any other forms of momentum. There's only one form of momentum, but there's all different kinds of energy. So, like, think about back to that explosion. Well, that kinetic energy came from, well, that chemical potential energy in that bomb. So energy can transform and change into other forms of energy. Momentum can't do that because there's no other forms of momentum, but energy can. So that brings us to the law of conservation of energy. In physics, the law of conservation of energy states that energy cannot be created or destroyed, only changed or transformed from one form into another, or transferred from one object to another. In other words, like momentum, energy cannot be created or destroyed. It can be transferred from one place to another. Energy can also transform or change into another form of energy. So like momentum is like money in this room, right? It can change hands, but it doesn't change the total amount in this room. I like to think of energy as if you're traveling abroad, the money that you have if you're traveling to another country. You go to another country, the first thing you have to do is exchange your currency. Well, you're not getting any richer or poorer by changing your money out, but you just have a different currency. So that's what energy is like. You have lots of different, and you can change them, but you're not creating or destroying any of that energy. You're not getting richer or poorer by going to another country and getting different currency. So let's look at elastic collision in terms of energy. So in terms of energy, an elastic collision is a collision in which there is no net loss in kinetic energy in the system as a result of the collision. So think about when they collide. Well, there's no energy loss to heat, no energy loss to sound. It's all just transferred from one object to another, right? It's all kinetic energy to kinetic energy before and after that collision. Now, inelastic collision, in terms of energy, an inelastic collision is a collision in which kinetic energy is not conserved due to the action of like internal friction and like that internal energy. So yes, when two objects collide, well, some of that energy is lost to sound, some of it is lost to heat, some of it is like internal energy. So that's the difference, right? That's the difference between inelastic and inelastic collisions in terms of energy. So just as a final thought, remember, there's too much unknown in the universe to take a break from learning. Get out there and question everything.